Welcome to this presentation on the impact of medium access delay and belief consensus for target tracking. This is joint work with colleagues from Chalmers University of Technology, High IQ Consulting and Linköping University. My name is Henk Wijmeers. When distributed particle filters are used for target tracking, belief consensus is often employed to achieve agreement on the particle weights. The convergence properties of belief consensus are known and indicate that high connectivity is beneficial. However, little attention has been given to the impact of medium access delays, where high connectivity leads to more interference and thus larger delay. One study showed that asymptotically, the communication range has no impact on the convergence properties. Here instead, we focus on small networks with realistic operating parameters. This will be the outline for today. We will start by reviewing the system model and the standard distributed particle filter, which relies on a consensus algorithm as an inner loop. We then describe how we compute the MAC delay and show performance results regarding the accuracy-delay trade-off. We end with conclusions. We consider a single mobile target with a prior on the state that is known to all the sensors. The target moves according to a known mobility model. The NS sensors periodically obtain observations that are dependent on the current state of the target. Measurements are assumed to be independent given the position of the target. Sensors can communicate with neighboring sensors within a certain communication range. To track the state of the target, the sensors employ a distributed Bayesian filter, which represents the belief of the target state in terms of a number of particles with associated weights. In particular, every sensor has the same set of particles, so every sensor can perform the same prediction based on the mobility model. In contrast, every sensor has its own measurement with associated likelihood function. In order to maintain the same set of particles at the next time step, the sensor must have access to the product of all the likelihood functions, evaluated in every particle. This product is computed through a consensus algorithm. This leads to a natural breakdown of the distributed particle filter in first local processing, involving resampling, predicting, and measuring, followed by joint processing to achieve weight consensus. Revisiting our tracking application, the goal is to compute the sum of the log likelihoods evaluated in every particle. Running average consensus until convergence and then multiplying the solution with the number of sensors solves the problem. However, in practice, we must stop after a finite number of iterations. To still achieve exact consensus, which is required to maintain the same particles for every sensor at the next time step, assuming suitable seeding of the random number generators, we follow the average consensus with max consensus, which can achieve exact consensus after a number of iterations equal to the graph diameter. As an example, suppose we stop average consensus after a finite number of iterations. The sensors will have values close to the average, but not exactly equal to the average. Applying max consensus then gives exact agreement, though again not exactly equal to the average. Now we understand the operation of the distributed particle filter, we know that consensus requires broadcasting of information. To organize these broadcasts in a collision-free manner, we must rely on a medium access control protocol. Here we consider time division multiple access with spatial reuse. The total delay is denoted by t and expressed as a function of the following. The number of TDMA time slots required for a single iteration, which can be computed by solving a classical node coloring problem. The number of consensus iterations, where I denotes the number of average consensus iterations, and dr is the graph diameter, which is the number of max consensus iterations. And finally, the time to send a single packet, which depends on the data rate, the number of particles, the quantization level, and the number of bits per packet. We now put everything together and simulate a network with 25 sensors on a grid and one mobile target. We fix the communication parameters to reasonable values and vary the number of consensus iterations. We also vary the communication range, giving rise to different network topologies, shown on the right. In addition to the delay, we also care about the accuracy of the distributed particle filter. As a distributed particle filter can never do better than a centralized particle filter, which has access to all the likelihoods, we compute a relative error. This error can be interpreted as follows. If the relative error is around 1, the distributed particle filter gives rise to an additional absolute error that is of the same order as the absolute error of the centralized particle filter. When the relative error is about 0.1, the additional absolute error induced by the distributed particle filter is only on the order of 10% of the error of the centralized particle filter. Here we show an example track in blue. The estimates of the centralized particle filter are shown in green stars and are close to the target after around 20 time steps. The distributed particle filter with I equal to 0, which means that it only performs max consensus and no average consensus, has poor performance for all times. Increasing the number of average consensus iterations improves the performance, and the distributed particle filter is able to achieve the same performance as a centralized particle filter. To show the delay accuracy trade-off, we plot the time to run belief consensus as a function of the relative error for different values of the communication radius and different number of average consensus iterations, from 0, 1, 2, 4, 8, and so forth. When no average consensus is run, the relative error is large and independent of the communication range, while the delay depends on the network topology. In particular, the delay depends on the graph diameter, which leads to smaller delays for larger communication range, and on the amount of spatial reuse, which leads to smaller delays for smaller communication radius. It should be noted that for our specific example, the largest communication radius leads to the smallest delay, but this is no longer true when the number of nodes is increased, as the impact of the graph diameter will be reduced. When one average consensus iteration is performed, the error is reduced in all cases, but at a cost in terms of delay. The larger the communication radius, the faster the error goes down. For a communication radius of 114 meters, all the sensors can communicate directly with all other sensors, and the relative error can be shown to be 0. Increasing the number of average consensus iterations to 2 or to 4 results in a very small decrease in terms of the error for the small communication radius of 20 meters. We see that care needs to be taken when designing the sensor network in order to meet a target delay accuracy performance. In conclusion, we found that scheduling delays in the distributed particle filter can be significant. The delay depends on different effects, including the graph diameter, the amount of spatial reuse, and how aggressive the step size is in average consensus. For the case we considered, we found that when the number of nodes is not too large, high connectivity is beneficial in terms of the accuracy-delay trade-off. For more information about this research, please see our conference contribution and our website. Thank you and goodbye.